So yesterday, for those of you who are paying attention, what I had said was that this mixing layer example, okay, this is a lot like jets. Actually, this is not like jets. Of course, when you have this U1 and U2 that are different, then you should think about it like a plate in between, and then a flat plate boundary layer where the plate has a velocity of where plate has some velocity. Okay, the velocity of the plate doesn't remain constant, and the idea here is that there is a shear stress here. So there is a velocity deficit of u1 minus u2 at y equal to 0. Okay, so this velocity deficit at y equal to 0, this is what diffuses upwards. Okay, and of course the velocity deficit will not remain constant at y equal to 0. So this is at x equal to 0, and as you move ahead, the velocity deficit will change a little bit, and you see a diffusion of velocity, basically something like this. Okay, so you see that this profile as you move forward becomes smoother and smoother. So this is actually case which is very similar to flat plates and not free jets, and you can look at the boundary conditions that we have used. You can confirm that the momentum integral is not constant in these. Okay, momentum integral will not be constant, so rho u square dy is not constant here, and you will have to use the boundary layer boundary conditions, the Blasius boundary conditions, which are that the velocity. So you know the velocity at y tends to infinity, and at this interface you will have to use that u1 for y equal to 0 for all x is equal to u2 for y equal to 0 for all x, where this region is 1, this region it's 2, and then there is another boundary condition which is for an interface, which is from the stress boundary stress equality. So you have basically T dot n at 1 is T dot n at 2, which will give you that mu 1 del u1 over del y at y equal to 0 is equal to mu 2 del u2 by del y. Okay, there will obviously be another condition. This you will get from the stress boundary conditions. Okay, so you have to use these, and then you can convert this system into a Blasius type of a system. So this is called a mixing layer, or in some places you may also see it as being called a shear layer. Okay, the name is in a way self explanatory. There is a shear that is diffusing as you move downstream. Okay, and so a jet is a combination of two shear layers, because in jets, let's say you have this and this is constant. Okay, and as this jet proceeds, basically here you see a shear layer which is developing. Okay, and bottom also you see a shear layer that is developing, because at the top the condition is something like 0 velocity and then a u naught, and bottom the condition is something like velocity of u naught and then a 0 velocity, and this is what diffuses forward. Okay, so those of you who were paying attention, please fix this in your notes. This is not like jet, this is more like flat plates. Actually, you can prove, basically you can, once you show this, then you know that p plus q equals 1 was holding, right, in our self similar assumption, and that's pretty much it. That's all you can get. And then since there is a diffusion phenomena that is happening here, okay, since there is a diffusion phenomena that is happening here, you will see that p and q will have to be half. So that should also tell you that jets are, so these are like shear layers. Okay, these are not exactly shear layers, because we know that jets have an entrainment also. Okay, here you will see some y velocity, but that doesn't mean that your momentum integral will be constant. So you have to do that analysis to convince yourself. You can find this analysis in, I think, Frank M. White's viscous flow textbook, and then basically this is all you can get. You will form a Blasius type of an equation in region 1, you will form a Blasius type of an equation in region 2, and that's it. It's a nonlinear equation, you cannot solve it analytically, you will have to solve it numerically. And then you will have to connect these boundary conditions, interface conditions. Okay. So now let us resume with what we were trying to do, that was hydrodynamic instability, or stability if you want to really think about. And our discussion was something like this, that all of the solutions that we have been considering so far, linear or non-linear, so we have looked at non-linear solutions in boundary layers. Before then, all of our equations, governing equations, we were making the approximation so that we reach linear equations. Okay, if you recall the impulsively moving plate and all of those examples, there we made a lot of simplification assumptions so that the eventual equation, the simplified equation, was a linear equation, right? In boundary layers, we started looking at nonlinear equations, and then we saw that cell similarity is our best tool that we have. We really don't have a lot of other options, but the idea is that self similar solutions are not the only solutions. These are the nonlinear equations. So a nonlinear equation is bound to have multiple solutions. Okay, a nonlinear equation is bound to have multiple solutions, and a good example of that is a pendulum. So if you have a pendulum, let's say you send it to angle theta, this is L, this is M, then we saw that the governing equation of this guy is minus G over L sine theta. This is a nonlinear equation. This is a nonlinear equation. There are two in the standard argument space. There are two solutions of this equation. One is steady solutions of this equation. One is theta equals 0 and the other is theta equals pi. Both are steady solutions, but one is unstable, and so you never see it in the reality, and the other is stable, and you always see it in the reality, or more often you see it in the reality. You will never find pendulums which are going like this. Okay, so one is stable, one is unstable. So what we have to do is, so let me exemplify a procedure from this part. So let us say that theta naught I consider as the steady solution. So theta naught equals 0 is the steady solution, and theta naught equals pi is another steady solution. So in hydrodynamic instability, what we tend to do is, so I'm giving an example of pendulum. Of course, pendulum is not a case of hydrodynamic instability, but what I'm trying to convince you guys is that this type of analysis is irrespective of fluids or anything. Okay, this type of analysis is there for any dynamical equations. Any dynamical system that you have, you can do this dynamical stability analysis that we are going to look at. So let's say you have theta naught equal to 0 and you want to look at stability of steady solution, that is theta naught equals 0. So what you say is, okay, let us consider that my theta is some theta naught plus an epsilon theta prime, where epsilon is much less than 1. Some epsilon doesn't have to be, you don't have to recognize this epsilon in terms of the variables of the problem. It can be some epsilon, and order of magnitude of theta prime is equal to, let's say, order of magnitude of theta naught. Of course, theta naught is 0 here, but that doesn't mean the order of magnitude of theta naught is 0. Theta naught can take any values from 0 to pi. So by saying this, I am trying to say that order of theta prime is 0 to pi. Okay, basically theta prime is not small. I am making it small by multiplying it with a small number. Okay, and then let us substitute this in our governing equation. So we have theta naught plus epsilon theta prime double dot equals minus g by L sine theta naught plus epsilon theta prime. Okay. By definition, theta naught is a steady solution. By definition, theta naught is a steady solution. So, by definition of theta naught, by definition, theta naught double dot is 0. Okay, we are looking at stability of a steady solution. By definition, theta naught double dot is 0. So, on the left hand side, we are left with epsilon theta prime double dot equals minus g by L. Now, here you can do it two ways. We can either expand right here, or you can, you know, so let's not expand right here. Let's just break it into sine and cosine. So, we have sine theta naught cos epsilon theta prime plus sine epsilon theta prime cos theta naught. Okay. So, epsilon theta double dot theta prime double dot is equal to, so what, how can I expand cos epsilon theta prime? What is the Taylor expansion of cos epsilon theta prime? Epsilon is much less than 1. So, this is a small number. So, what is the expansion of cos? What is the expansion of cos? 1 minus epsilon theta prime square by 2 and so on. What about sine epsilon theta prime? Epsilon theta prime minus by 3 and so on. Okay. Now, as we do what we in this course, we what we will say is, let us linearize the equation. Technically, we are linearizing the equation about theta naught. Okay. Linearization has to be done about a point, because whenever you do a Taylor expansion, the Taylor expansion is about a point. So, here you are doing Taylor expansion of this variable. So, it is epsilon theta prime, you are doing it an expansion about 0, but technically you are writing this whole as an expansion of sine theta naught plus epsilon theta prime. You are writing this expansion about theta naught. Okay. So, what will we get? Linearize means keep order epsilon terms only. Okay. So, on the left hand side we have epsilon theta dot double prime, and on the right hand side what do we have? We have minus g by L of sine theta naught, okay, and then rest we will get epsilon square terms, and then plus a cos theta naught times epsilon theta prime, and then we have higher order terms. Okay. Now, by definition, again by definition of theta naught, irrespective of theta naught being 0 or pi, okay, let us forget that we are looking at stability of theta naught equals 0. Let us just take any theta naught, either of them, irrespective of them being 0 or pi, we know that sine theta naught is going to be 0, because the definition of theta naught is that it is a steady solution, and sine theta naught is minus g by L sine theta naught is nothing but theta naught double dot, which is 0 by definition again. So, by definition of sine theta naught, we have this guy is 0, and we are left with epsilon theta prime double dot equals minus of cos theta naught g by L epsilon theta prime. So, for theta prime we have the linearized equation as minus g by L cos theta naught theta prime. Okay. For theta prime we have this linearized equation. So, for theta naught equals 0, we see that we have cos theta naught is 1, and for theta naught equals pi, we have, okay. So, we have done a linearization of our governing equation, which was this, about a steady solution theta naught, which we have derived earlier. Okay, we have done a linearization of governing equation about theta naught. That is very important to remember. We are always doing linearization about a known solution. Whenever we study stability, it's always linearization about a known solution. Okay, so how do we infer stability from here? What we will do is, let's write theta dot prime as some omega, and then omega or omega prime, and then omega dot prime is minus g by L theta prime. And what I can do here is that I can write it as theta prime omega prime dot equals, and I can write this in the matrix form, 0 1 minus g by L 0. Okay, and here, as you can imagine, you will get a system like this: theta prime omega prime dot equals 0 1 g by L 0. Once you have this system of linear ODEs, how do you infer stability from here? How do you infer stability from here? Hmm? How do we infer stability from here? Once we have, so this is a system of two linear ODEs. How do we infer stability from here? Okay, first of all, what are the general solutions of these type of equations? Huh? How do we write a general solution of these type of equations? Hmm? Any ideas? Huh? How? How do you use eigenvalues here? Hmm? How do we use eigenvalues here? I mean, instead of trying to recollect, which is oftentimes a mistake that we do, if you forget anything about, let's say, you just know calculus, so how will you tell me the solution of these equations? How will you tell me what is the solution of a system of linear ODEs? Instead of trying to recollect, how do we find the solution of these equations? This you guys have covered in your maths 1 and 2 courses. Okay, so the way you write down a solution of these two equations is, so we'll show that in a minute. So let me just give you why that, let me just give you the solution, and a general solution here will be some constant C1 times the eigenvector of this matrix, let's call it V1, times e to the power lambda 1 t plus C2 V2 e to the power lambda 2 t, where this lambda 1 comma V1 or lambda I comma Vi are eigenvalues and eigenvectors. To be specific, write eigenvectors of the matrix, of which matrix? Of this matrix plus minus G. Okay, and so what are the eigenvalues of this matrix with a plus minus GL? The eigenvalues here, you will form the equation as lambda square minus plus G by L equals 0, right? So lambda square is equal to actually plus minus G by L. Okay, for a plus sign you have lambda equals plus minus I, for a minus sign you have lambda equals plus minus I root G by L, and then for a minus, for a plus sign you have lambda equals plus minus G by L. Okay, so this is for theta naught equals 0, this is for theta naught equals pi. So there are two types of eigenvectors that you can define. there is this definition of eigenvectors and eigenvalues. Okay, just to make sure this is not index notation, there is no summation on the right. I have put it on the superscript, and then you can also define, let's say, let's not write them as v, let's maybe write them as u. You can also find this. Okay, and maybe some of you who are linear algebraically a little bit more agile, in which case will these two be equal? In which case, what is the condition on A when left and right eigenvectors are equal? So, these are right, these are left by basic multiplication, that this is pre multiplied, this is post multiplied. When are they equal? When A is symmetric. Okay, when A is symmetric, then this guy is just a transpose of this. This is a column, this is a row of the same column. You just invert it, transpose it. Okay, so in general, when A is not symmetric, you can't say that. Okay, so from here, what do you see? That you have two values of lambda that are possible, and one of them is going to be positive. One of them here is going to be positive. You put that here, you are going to get an exponentially blowing up solution. You are going to get a solution which is exponentially increasing in time. Okay, so the moment you see a lambda value which has a real part greater than 0, this means solution blows up in time, or basically what we are trying to say is that some kind of a norm of the solution. So, some kind of a norm of the solution, let's call this as our solution vector y. So, some kind of a norm of our solution is going as lambda t. What kind of norm is not really a point of discussion for this course. Okay, you can identify if your real of lambda is greater than 0, any lambda, any eigenvalue which has a real part that is greater than 0, and this is your general solution, it's going to blow up in time. It's going to grow to infinity in time. Basically, blowing up has a lot of different definitions in maths. Okay, there are many definitions that you can think about. One of the definitions is that you can always find a number. Okay, you can always find a time when this is greater than arbitrarily large number. Okay, you can think about something growing up to infinity as this, that you can always find a finite time when the solution's norm is greater than any arbitrarily large number. Okay, so that means at that time the solution would be infinity. So that means within the confines of linear analysis, what you have is that the solution is growing in time. Now there are some caveats here, and the caveats are, if you recall what we did in our analysis, we said that your theta is theta naught plus epsilon theta prime. We said that theta prime is of order, so or order of theta prime is order of theta naught. Theta prime is not allowed to grow to infinity, but it is still going to grow to infinity within the confines of linear analysis. The idea is when theta prime is so large, and it's so large that epsilon times theta prime is not small anymore. In that case, you have to account for the nonlinear terms which you have dropped here. In that case, you have to account for the nonlinear terms which you have dropped here, and once you account for the nonlinear terms, you will get solutions which are not blowing up to infinity. Basically, what is this solution trying to say? For theta naught equals pi, there is a solution which grows to infinity. What does it mean? If you start a pendulum here and give a small perturbation, it's going to just keep rotating for an infinite amount of time. The angle of its rotation is going to increase in time exponentially forever, right? But the analysis you did requires that the theta prime order is not infinite. Okay, or you can think about that the order of epsilon theta prime is small than theta naught. Okay, the perturbations are small. When the perturbations are small, the solution is growing to infinity, growing exponentially in time, but when the perturbations become large, then your nonlinear terms become important, and you can't say that your solution obeys this solution form. Then you have to derive further corrections in your solution. Okay. So, growing up to infinity should be claimed with a caution that it is not going to grow up to infinity for an infinite amount of time, because after some time, if a solution is growing, it will cease to be linear, it will cease to be small enough that you can apply a linearization approximation. Okay. So, this growing up to infinity in time has to be claimed very carefully, that it has to still be small, and you will see an exponential trend. Okay. So, based on this analysis, we can actually form a generalized theory uh, for a very specific type of systems. This was an analysis for pendulum, which is a simple, oh, by the way, maybe let me just explicitly say. So, from here you see that theta naught equals 0, both lambdas are purely imaginary, there is no real part. So, there you get purely oscillatory solution. Here you get exponentially increasing solution. So, in this case the steady solution that you took is called neutrally stable steady solution. In some textbooks, or probably in our lectures ahead also, we are going to call this steady solution as base state. Okay. So, there is a base state of our system, and we are linearizing the equations about that base state to understand the stability of that base state. You may have multiple base states. Okay. This is a neutrally stable steady solution or base state. This is a linearly unstable steady solution or base state. If you had eigenvalues which had both of them which had real part as negative, then you would have linearly stable steady solution or base state. Okay. Then you would have linearly stable solution or linearly stable base state, and using these as our guiding steps, we can formulate a general theory, and the theory goes something like this. Let us say we have a system of n dynamical equations for a system. Okay. For a dynamical system, and the equations are that d by dt of y1, y2, yn is equal to f1, which could be a function of y1, y2, yn and time as well, f2 and so on, fn. Let us say you have this. Okay. We are going to say that we are looking at systems where these f1, f2, fn are not explicitly functions of time. Of course, time could be a parameter which is changing y1, y2 and so on. They are not explicitly functions of time. What are these systems called? When you do not have the right hand side explicitly a function of time. For example, here we had a pendulum where you had minus g by L sin theta. Now, some of you may say, oh, sin theta will change when theta is changing in time. You are right. Right hand side is changing in time only due to its dependence on the degrees of freedom. If I had the pendulum, on a support, that support was itself oscillating in time with its own frequency, then you can show that that g, okay, due to the reference frame being accelerating, that acceleration due to gravity g would be actually changing in time. An effective acceleration due to gravity would be changing in time, and that would be explicitly changing in time. not due to change in theta. Okay, if you consider a pendulum like this, and here you have this guy oscillating with some amplitude, let us say its y is some y naught sin omega t, then you can show that the equation for this type of a pendulum is some minus g, let us say g bar, which is a function of t times sin theta. Here you have a right hand side which is explicitly changing in time, even if theta is not changing in time. So, we are going to say that that is not the case for us. Those systems are called autonomous systems. Autonomous systems. Basically, the right hand side, which I can concisely write like this, is essentially varying with time just as a parameter. Okay, it is not explicitly changing in time. So, we are going to look at systems which you could write concisely like this. Okay, and you could write this type of a dynamical equation for any system. These are a system of n ODEs. Okay, you could have a pendulum with two, you could have a double pendulum, triple pendulum, you could write 3 equations, you could have spring mass systems of any degrees of freedom, you could write, if there is n degrees of freedom, you could write these n equations. Okay, there is a connection from here to hydrodynamics. Okay, and the connection from here to hydrodynamics is that when you look at fluid dynamic equations, those are basically similar equations with n tends to infinity, because you have PDEs. You can look at PDEs as ODEs at multiple points, at infinite number of points. So, in fluid dynamics, this whole thing will be very useful. So, let us wait for few more lectures to see that how. So, if we have a system of equations like this, then let us say let y naught be a steady solution of the system. That means dy naught over dt is 0, or f of y naught is 0. Okay, f of y naught is 0. So, now let us say that let y prime, or rather epsilon y prime, be perturbation to y naught. So, let us look at y when it is y naught plus epsilon y prime. Okay. Let us substitute this in our governing equation. We get d by dt of y naught plus epsilon dy prime by dt equals, we have f of y naught plus epsilon y prime. Okay. By definition, this guy is 0. The perturbation that I am considering, I am taking that this epsilon is much less than 1. Have you guys covered this in dynamical systems in your courses on dynamic multi-body systems? I don't know. Huh? Have you looked at this? Have you looked at stability following this kind of a procedure? Okay, so then I'm not doing something new to you guys, hopefully. So, if some norm of epsilon y prime and some norm of y naught is a quantity which is much less than 1. Okay, if this holds, if the perturbation is small compared to y naught, then you can write down the Taylor expansion of your f And what is the Taylor expansion of F? What will be the Taylor expansion here? What will be the Taylor expansion? F of y naught plus epsilon y prime. This is a vector. So here this vector is not Cartesian vector. This is a tuple essentially of n cross 1. So how do I write here? How do I write this system consistently in the matrix form? So you actually have to write it like this, where this is a matrix A evaluated at y naught, or let's call it as J, times epsilon y prime plus higher order terms. Okay, and this J is basically evaluated at y equals y naught. You can think about the components of J, and they will be essentially this J is called the Jacobian matrix of the system. Of the system at y naught. These are important points because Jacobian matrix will not be same for all fluid flows. As you will see, Jacobian matrix will be different for different fluid flows based on what is the base state and what are the different boundary conditions as we go into that. Okay, so Jacobian matrix is different for every system, basically for every problem, and if you have multiple base states or multiple steady states of the problem, it will be different for all of those steady states as well, because it's eventually a function of this y naught. Okay. So now let us substitute that in our dynamical equation. We have del dy prime by dt equals, so let's substitute our Taylor expansion. So linearize. So when we linearize, we consider only epsilon terms and not any other terms. So we have anyways not been writing them. So we get dy prime by dt equals, what is f y naught by definition? F of y naught is 0 by definition. So you get j y naught epsilon, oh epsilon gets cancelled, times y prime. So you can also write it like plus order epsilon square if you want. And now this equation you can also think about it as dy prime by dt equals, okay, I mean I'm not trying to, I'm trying to just ignore that. Okay, let's write it as j naught. Okay. Let's talk about that after the class. Okay. So once you have this, then let j naught be written as, or let's not assume it can be written as, let's show that you have, let's say, these eigenvectors, the right eigenvectors for your J matrix. Okay, let us say your Vk is the kth eigenvector and lambda super k is the kth eigenvalue of this matrix. Okay, then what you can do is you can arrange your eigenvectors like this. You can arrange the eigenvectors as column vectors in a matrix, and if you multiply like this, then you will get lambda, or you rather you will get lambda 1 v 1, lambda 2 v 2, and so on. In this right hand side, you can also see it as lambda 1, lambda 2, lambda n times this same matrix that you will get by arranging eigenvectors as column vectors, as columns of the matrix. So, you can write this J as, so let's say this is a matrix which I write as V equals a lambda matrix which is a diagonal matrix times V. Hmm? Which one? Which V? Small v or capital V? Capital V is a matrix. So, matrix that has each column as a different eigenvector. You can also write this, since lambda is a diagonal matrix, you can also write this like this actually. Uh, right? You can write this matrix, this multiplication, you can write it like this also, right? Or no? Hmm? Can we write it like this? So, let us say u1, u2, u3, v1, v2, v3. So, from here we get lambda u1 lambda, oh, hold on, actually you can, my bad, this multiplication you can write, because you have to multiply this lambda only with v1 components, right? So, this is actually, you can write it like this only. I had written it incorrectly, times a matrix lambda 1, lambda 2, lambda n. Okay, so if you put this guy here, then we have u1 times this, that's it, and then here we will have lambda times v1, okay, yeah, lambda 2 times v1, and so on. So, yeah, you can write it not like lambda times v, but actually like this, and then I can post multiply with v inverse. When can I have a v inverse? When is a v inverse going to be possible? Hmm? When is a v inverse even going to be possible? Huh? No, no, I mean, I have taken this as an example. When v has a rank n, when does v have a rank n? So, all the eigenvectors have to be linearly independent. When is that going to be the case? When the eigenvalues are all unique. Okay, when the eigenvalues are all unique, you will have linearly independent eigenvectors. Once you have that, your matrix V will not have any rank deficiency, it will be full rank matrix, and then you can formulate, basically V will not be singular, and then you can write an inverse for that. So, let us substitute that here for this J naught matrix. So, what do we get? D y prime over dt equals, let us write it like this, V lambda V inverse d y times a y prime. Now I can pre-multiply this equation with V inverse, and since V inverse is constant in time, remember V inverse was formed by eigenvectors of J naught. J naught is constant in time because in J naught you have already substituted the base state, it is a function of Y naught. So, V inverse is going to be constant in time. We are going to deal with that also only. You can formulate the same theory for J being explicitly varying in time also. Okay, let me just say that explicitly, that all of the theory that we are going to discuss, we are looking at some special cases which are relevant to us for this course, but you can formulate this theory when J is explicitly varying in time as well. So, then we can write this equation as d by dt of V inverse y prime equals lambda times V inverse y prime. Now, it is an assumption within autonomous system case. It's not an assumption if you are solving an autonomous system. That is going to be the case if you are looking at an autonomous system. If we have non-autonomous system, of course J will be varying in time. Okay, and there are ways to do stability analysis of those kind of systems also. For example, in this case, you can obviously guess that this G bar as a function of time will be an oscillatory function. Okay, if your J matrix is an oscillatory function of time, it has a time period t, then you can formulate what is known as flow case stability analysis following this discussion only, but we are not going to go into that detail. Now, notice what I have done here. Some of you may know what I have done here. Basically, instead of y prime, if you consider a matrix, a vector, let us call it as some x, which is given by this V inverse times y, then what I have essentially done is I have converted my coupled system of equations. So, this lambda matrix is a diagonal matrix. So, if you look at this system, you will have dx1 by dt equals lambda 1 x1, dx2 by dt equals lambda 2 x2, and so on. From a coupled system of equations, first I did the linearization. After doing the linearization, I diagonalized the system. This is called diagonalization of the system, where I decoupled all the equations. I considered new linear combinations of variables so that the equations are decoupled. For example, if I give you an equation like this, let us say dy1 by dt equals y1 y1 plus y2 and dy2 by dt equals y1 minus y2, then what can you do here? Or rather, let us consider a simple example. Here it is y2, here it is y1, direct coupling, there is no self dependence. Then you can formulate a linear combination of y1 and y2, which is, let us say, y1 plus y2, and that will be equal to y1 plus y2. And you can formulate another linear combination, which is, let us say, y1 minus y2, and that will be equal to minus of itself. So, by looking at this, you basically do some linear combination of these degrees of freedom and you find a decoupled system. That is what we have done here in a more general fashion. And so, from here we know that each of these xi's are going to vary as some constant ai, or let us say equal to, let me keep writing this as superscript so you do not confuse it with index notation, lambda I t. Okay. So, your x solution will be some, let us say, a how do we write this? Hmm? We can write it as diagonals actually. Yeah. So, you can put lambda 1 t lambda 2t and so on, and then you can put your constants here. Okay, and now you see that your some norm, let's say the L2 norm, which is nothing but square root of x1 square plus x2 square plus x3 square, will grow in time if at least one eigenvalue or any eigenvalue, let's call it, if any eigenvalue, let's say kth eigenvalue, has a real part which is greater than 0. And if that is the case, then you say that the steady solution y naught is an unstable steady solution of your dynamical equation, linearly unstable solution of your dynamical equation. Then this implies y naught is linearly unstable solution of dy by dt equals f of y. Okay, this y naught is linearly unstable, is a linearly unstable solution of dy by dt equals f of y. Now, how is all of this connected to fluid dynamics? As we will see that in some cases the laminar flow solutions that we have found, even the simplest laminar flow solution, which is, let us say, your flow in a channel. Okay, if you have, let's say, this is y equals h, you have y equals minus h, then you know that this variable, this profile is parabolic in nature. Even in the simplest of these kind of examples, if you give some form of perturbations, if you consider some form of perturbations, they will be unstable. You will see that there is a stability regime of this kind of a flow. Okay, and in terms of fluid dynamics, you will see that as you increase your Reynolds number and all of those things, the stability regime basically changes. Okay, some form of perturbations will grow to infinity at some particular or after some particular Reynolds number, after a critical Reynolds number, for example. There is a critical Reynolds number after which you will see that some perturbations start growing to infinity. So you say that kind of a flow solution, it's not like it's not a solution of the governing equations, but it is an unstable solution of the governing equations. And in reality, it may be very hard to see it. Okay, governing equations are non-linear. You have found a solution. There are hundreds of other solutions that are possible. You don't know hundreds, thousands, we actually don't know anything about this type of equations. So that's the power of hydrodynamic stability. What it tells you is that, okay, you have found theoretically some solutions. What are the chances of you seeing it in reality? Okay, if you find that that solution is unstable, then the chances are close to nil. Okay, so what it would mean is, let's say, in, for example, in this particular case, we will see there is a critical Reynolds number after which you have an unstable solution. This is an unstable solution after a critical Reynolds number. So physically what it means is that through a channel, you cannot keep a laminar parabolic flow profile after this critical Reynolds number. There will be some other type of a solution which will break the assumptions that you have made when you try to derive this. Okay, so that is the essence of hydrodynamic stability. Next class we will start looking at how to apply all of this in fluid dynamic equations.